In this video, we're going to take a look at vectors. Right now, you may be used to vectors in many of your science and engineering courses, and you might be told that a vector is a quantity that has direction and magnitude, and that's a completely valid way of looking at it. But that way of looking at a vector is limited in the sense that it requires a certain geometry in order to understand it. So when you talk about like a directed line segment, you're talking about a geometric quantity. Now, when you look at vectors from an algebraic standpoint, that's where you start to see the certain algebraic properties that really define what a vector is. And that's what we're going to focus on, like the algebra of vectors. That's not to say that geometry isn't useful, but again, it's limited because geometry tends to be, visual. Like for us, it's two or three-dimensional geometry. But what about 4 dimensions or 5 dimensions, right? Algebra will work fine in any of those dimensions, but geometry fails. How do you graph something in 4 dimensions, all right? So let's start with a couple definitions, some of which might seem familiar to you, but others might be a little bit more general than what you're used to. So we use this symbol, and I'm sure you've seen this symbol before, this R2. We use this to represent the set of all vectors in the plane, right? So R2 is used to represent the set of all vectors in the plane, meaning these are two-dimensional vectors, right? So these are two-dimensional vectors. Now, as far as a 2D vector is concerned, well, it usually has two components, an x component and a y component, right? So let's see if we can represent that symbolically. So it's a set, so we're going to use our braces. Now, there's several ways that you can represent vectors. You can represent them, for instance, like this, like as a single column, and let's say you have like a x1 and an x2 there, such that your x1 and x2 can be any real numbers, right? So x1 and x2 can be any real numbers, right? You could do it like this. Other ways that you can represent a vector, you can represent it as like a just coordinates like this. x1, x2, again, where x1 and x2 can be any real number. Sometimes I know, like in certain, like multivariable calculus, for instance, you might represent vectors like this with these angled brackets, right? So these are all equivalent forms of the same thing. So it doesn't matter if I use square brackets or parentheses or angled brackets. It's the notion that I am representing a vector in the plane, and these are the components. So we refer to x1 and x2. So x1 and x2 are the components of the vector. Right? And it makes sense that if you're in 2 dimensions, right, you should have two components. And then, of course, again, I know it sounds like I'm trying to give geometry a bad name, but I'm not. So just as an example, and now for vectors, we usually use symbols like U, V, W, and they're usually written as lowercase and in bold type. Well, since I can't write in bold, what I'm going to use the little harpoon on top to indicate a vector, right? So we usually use like U, V, W, or U1, U2, and so forth. So let's say I'm going to use the column notation. right? So this is the vector u. Well, we can actually represent this geometrically, right? Now, when you talk about a vector as opposed to like a point, the vector, let's see here. So the first component of the vector is usually represented on the horizontal axis. So there, I'm going to put a 1 there. And then the second component on the vertical axis, I'm going to put a 2 there. And to draw this vector, I'm going to have the initial point of the vector at the origin, and then the final point of the vector at the point 1, comma 2, right? So this would simply be the point 1, comma 2. Now the vector that goes from the origin to that point, that directed line segment right there is what we would use to represent that vector u, right? And when the vector has an initial point at the origin, we call that that's the kind of the standard form, right? So this is the standard representation of u. Right? So this is the standard form of u. Right? And that's when it starts at the origin and then it ends. So the final point of the vector is going to be the point at which your x and y coordinates form that point, right? Now, as long as I don't change the magnitude and the direction, I can represent this point in this vector in different ways. So for instance, let's say I have it starting at, instead of the origin having start at the point 2, 1. So if it starts here, then what I would have to do is make sure I go over 1 unit and up 2 units. So basically there, right? That would be another form of the vector u, not in standard form. And then if I wanted another form, let's say I wanted it to start over here. Again, I could have it start at this point, go over 1 and up to, so all like something like this. And notice when you look at them, they appear parallel, right? And what we would say is that these are all equivalent vectors because they have the same components, 1, 2. They just have different initial points, right? So these are what we call equivalent vectors, right? And that means they have the same components, but just different initial points. So they have the same components, but different initial points. And geometrically, what it means is that they point in the same direction. So essentially, they're parallel, right? Right, so those are vectors in R2. But again, even in our real world, we live in well, from what we can perceive anyway, we can perceive a three-dimensional world. So then it makes sense that we'd need a way of like extending this, going from 2 to 3 dimensions. And then we use a similar notation. I'm not going to do so much of these sketches, but we use R3, and let me just write it out symbolically. And again, I'll just go with the column notation. So this will be the set of vectors of the form x1, x2, x3, where in general x1, x2, x3 can be any real number, right? The same idea. You have your components, you could sketch them, you could talk about equivalent vectors. But what we want to be able to do from an algebraic standpoint is not be limited by just 2 or 3 dimensions, because there are some times where you need vectors that have more than 3 components. And then that takes us to Rn, right? So Rn are vectors in this form. x1, x2, dot, 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 xn. Where again, all the components, so the xi's are real numbers where I goes from 1 to n. Right? So I equals 1, 2, dot, 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 n. And this set of vectors is called the Euclidean n-dimensional space, right? So this is called the Euclidean, named after the famous Greek mathematician Euclid. So Euclidean n-dimensional space. And you might be thinking, why do I need this? Well, you know, I don't know if you know much about, for instance, relativity, but you might have heard of like space and time, like where time is the fourth dimension. So if you think about that, if you want to represent something that's at a particular space or position in space and at a certain time, then you would need 4 components, right? You need the typical either x1, x2, x3, or if you want to think of it as x, y, z, you would need those as your components of space, and then you would need your 4th component to represent time. So right there, you'd need 4 components, hence you'd have to get a higher dimensional space, right? And it's not just like space-time. There are many other things that you can represent using this vector form that requires more than just 3 components, right? Now, the nice thing about these vectors, and what our goal initially is how do we do algebra with these vectors, right? How do we do algebra? Well, it turns out these, if you think of them, these are simply matrices that have 1 column and n rows, right? So all those operations that we can do with matrices, right, we can do with these special vectors, right? So vectors in Rn may be thought of as n by 1 matrices. And that's why I've been using this sort of column notation, so that when it looks like we're doing something very different, but algebraically we're going to be doing a lot of the same operations, right? So these vectors in Rn may be thought of as n by 1 matrices. Therefore, the familiar operations of addition, subtraction, and scalar multiplication, right, are possible with these vectors. Right, so scalar multiplication. So all these operations are possible in Rn, right? So in other words, if we have 2 vectors in R5, well, how do we add them? We're going to add the corresponding components. But we couldn't add a vector in R5 to a vector in R3. Why? Because the dimensions would be different. You'd have a 3 by 1 and a 5 by 1, and we can't do that, right? So just using matrices, right, as a template, it allows us to carry a lot of those operations over. Now, not all of them will carry over. For instance, many of the matrix operations that we looked at required a square matrix. Well, we're never going to get a square out of these, right? Unless it's you're talking about R1, where you have a 1 by 1. But as long as it's 2, 3, or higher dimensional, then these objects will never be comparable to square matrices, right? So we won't be able to do things like inverting a vector. That wouldn't really make much sense, right? But we can certainly do some other operations. So let's just do a little example to kind of wrap this video up, which is really just an intro to this concept, right? Right. And what I'm going to do an example with 4-dimensional vectors, and I'm going to call them U. I'll write them as my column, so 1, 1, 0, 3. And let's say V is negative 1, 2, 4, 1. And W, right? These vectors, say 0, 0, 2, 3. Right? So let's say question 1, find 2u minus 3v plus w, right? So this example I will use just to show the basic operations, the scalar multiplication. So we're going to multiply u by 2, we're going to multiply 3 by v, then we're going to do this subtraction and this addition, and what we're going to end up with is another vector in 4 dimensions, another vector in R4. So let's write this down. So this is equal to 2 times my 1, 1, 0, 3 minus 3 times negative 1, 2, 4, 1, and then plus w, which is 0, 0, 2, 3, right? And as usual, we do our scalar multiplication before we add and subtract, right? Order of operations. So let's double u, and we'll get 2, 2, 0, 3. And I'll keep the minus and just distribute the 3. So that becomes negative 3, 6, 12, 3. And then I have my third vector there. W stays the same, 0, 0, 2, 3. And then, so we add and subtract the corresponding component. So I have 2 minus negative 3, that's 5, plus 0, so 5. 2 minus 6, let me write my 6 a little better. So 2 minus 6, that's negative 4, plus 0, so negative 4. 0 minus 12 plus 2, that's negative 10. And then finally 3 minus 3 plus 3 is 3. And this is the vector that's 2u minus 3v plus w, right? And we could do a little bit of vector algebra. So find a vector x in R4 such that 2u minus x is equal to v plus 3x, right? And again, we've solved equations that are similar to this for matrices. And again, if we just tell ourselves that these special things that we're calling vectors are just, again, special matrices that are just comprised of one column, then we can do problems like this using the same set of algebraic properties, right? So so what we can do is isolate the x first, and you could do this in different ways. I could add x to both sides and then subtract v from both sides. So I'll have 2u minus v is equal to 4x. Therefore, x is equal to 1/4 of 2u minus v. So again, this all these operations we can do, and so remember, u is this vector right here, the 1, 1, 0, 3. So we got 1/4 of 2 times 1, 1, 0, 3. And then the v vector is our -1, 2, 4, 1. So minus -1, 2, 4, 1. And then, so again, as long as we have the different properties, we have the associativity property, we have the distributive property, all those properties hold. I'll just go ahead and simplify what I have in the parentheses. And let's see what that is. So that is 2 minus -1, so that's 3. 2 minus 2, that's 0. 0 minus 4, that's -4. And then 6 minus 1, that's 5. And then distribute the 1/4, and then here is the vector x. So this is 3/4, 0, -1, and 5/4. Right? So just wanted to do a couple examples showing you, if we now just tell ourselves that algebraically that these vectors are nothing more than just column matrices, then we don't have to reinvent the wheel. We have all the algebra that we need previously based on our work with matrices, and we simply apply them to these new objects that we're calling vectors, right? So see you in the next video.